This video shows the simulations and experimental results that validate the efficacy of our collision cone control barrier function, C3BF. Using the acceleration-controlled unicycle model, Python simulations in different scenarios were performed to get various obstacle avoidance behaviors like turning, braking, reversing, and overtaking. For practical testing, we incorporated the C3BF with Copernicus mobile robot. We can see that, initially, the robot follows the reference trajectory, and as the obstacle comes inside the perception boundary of the sensors, the QP actively starts modifying the reference control inputs to avoid it. As soon as the obstacle is avoided, the QP again becomes inactive. This comparison shows the effectiveness of C3BF on a spline reference trajectory with a static obstacle on it. After smoothly avoiding the block, the robot again tracks the spline trajectory using the reference controllers. For testing our algorithm in a dynamic environment setting, we used another robot, Volta, to act as a moving obstacle. We tried different scenarios by changing the obstacle's pose and velocity, and interestingly we got different collision avoidance behaviors of Copernicus, like reversing, turning, and overtaking. Additional experiments with reference spline trajectory were also conducted, including multiple stationary, same-direction moving, and perpendicularly moving obstacles. Notice that even with a slight change in the initial conditions, obstacles were always avoided with different maneuvers. Moreover, braking was also observed in the scenario with multiple obstacles where an optimum circumnavigating path is difficult.
We verified our algorithm on the acceleration-controlled bicycle model by simulating it in Python. Using the Stanley controller, the car tracks the reference spline curve with an elliptical static obstacle and avoids it by circumnavigating. To further test C3BF effectiveness in a real-life scenario, numerical simulations were performed using the CVXOPT library on the Carla simulator with moving obstacles such as pedestrians and cars. Information about the obstacle was programmatically retrieved from the Carla server. A virtual perception boundary was incorporated to accommodate the range of perception sensors on real self-driving cars. Various situations were tested by changing the Carla environment, as shown. The side figure graphically illustrates the formation of collision cones on the obstacles as they are detected, and then the C3BF QP alters the reference control inputs to take out the ego vehicle from the course of collision, exponentially. Notice that whenever an optimal circumnavigating path is unavailable, like in the fourth case, the ego vehicle smoothly brakes, thus ensuring safety.
Please check out our manuscript for theoretical proof and technical details. Thank you.